problem 1 on the practice test is no algebra. It's just identifying intervals where the function's increasing, decreasing, finding the maximum point, the minimum point, and saying the maximum and minimum values. This is all the way back from section 3.1. And when we did this, we just broke the graph up into regions. The region to the left, in this case, of the first maximum point, the region between the first maximum point and then the minimum point, the region between the minimum point and the last maximum point, and the region to the right of the maximum point. So my first region to the left of the maximum point is -infinity to -1. And this is clearly an increasing interval. And so I'm going to put this in my answer to 1a. The middle interval between this maximum point and that minimum point goes from the x-coordinate of the maximum point, which is -1, to the x-coordinate of this minimum point, which is 0, and that's a decreasing interval. So I'm going to put that in my answer to part B. So that's -1 to 0. Third interval goes from the x-coordinate of this minimum point, which is 0, to the x-coordinate of that maximum point, which is 1. That's another increasing interval, so I'm going to put that in my increasing interval, put a union between. The last interval goes from the x-coordinate of the maximum point all the way to the end of the graph. That's going to be a 1 to infinity. That's another decreasing interval, so I'll put that 1 to infinity. In my decreasing, put a union between. I have two maximum points, so the coordinates of my maximum points are the -1, 3, as well as the +1, 3. And then we should probably say something like the maximum y value is y equal to 3, which occurs when x equals both -1 and +1. And then there's my relative minimum point. And I can say the relative minimum value, the relative minimum y value, this is maybe not worded so nicely, but it doesn't matter, is y equal to 2, which occurs when x equal to 0. On my next page, I actually have this typed up, and same answers, and I don't know that this is better or worse for the explanation of the maximum and the minimum points, but it doesn't have to be perfect. Just emphasize both the y and the x when you're finding the maximum, and relative minimum values. Now ugliness, the E problem on the test. There's going to be one E problem on the test. I thought I'd get it out of the way early. Need to find the derivative, the critical numbers, where it's increasing, decreasing, maximum, mins. No, I don't have to worry about any concavity with the E problem. So let me do this derivative real quickly. So for this problem number 2, I need the product rule to do the derivative because it's multiplication and both factors have an x. The first factor is 6x. The last factor or the second factor is e to the x. The derivative of 6x is just 6. And we've done this a few times. The derivative of e to the x is just e to the x. So I'm going to speed through that derivative. Cross multiply, put a plus between. So my derivative is going to be cross multiplying down 6x e to the x plus cross multiplying up 6e to the x. It's worth my time to pull out that common factor because it'll help me in part B. So the common factor of 6e to the x I'll pull out and be left with an x plus 1. That's going to be my answer to part A. So the derivative is 6e to the x times x plus 1. Part B wants me to find the critical numbers. So this was part A. For part B, I just set the derivative equal to 0. Goes 6e to the x times x plus 1 equals to 0. If you set the 6e to the x equal to 0, you don't get a solution. When you set x plus 1 equal to 0, you subtract 1 from both sides and get x equal to -1. That's going to be the only critical number. Now, to do everything else, the increasing, decreasing, minimum, and maximum, I need to do one giant computation. So the rest, for C through H, I can't do it individually. It kind of all comes out in one giant computation. So create a number line, negative infinity on the far left edge, positive infinity on the far right edge, the x coordinate of my critical value, -1, on that number line. Create my interval, negative infinity to -1, and then -1 to infinity. Pick a number but up to the edge here for my testing, and I check -2 and 0. Plug those numbers into the first derivative. See if you get a negative or a positive sign. Plugging it into that derivative, I'm going to get 6e to the -2 times -2 plus 1 for my first computation. And then for my second computation, 6e to the 0 times 0 plus 1. This is the one I could do in my head because e to the 0 power is 1. This gives me 6 times 1 times 1, which is 6. The second one, it's 6e to the -2 times -1. I cleaned this up just because I'm not that good at entering this on my calculator. This simplifies to -6e to the -2. That I could enter better on my calculator. So -6 second ln e to the -2, and it's -0.81. Doesn't matter how accurate I am in terms of the decimals, I just need to be accurate in terms of the sign. This interval, because I got a negative, the graph is going to be decreasing. The second interval, the graph is going to be increasing because the result of plugging the critical number into the derivative was positive. So for my answers, the increasing interval is -1 to infinity. The decreasing interval is -infinity to -1. So this graph goes decreasing, increasing. So this is a minimum. I would need another critical value to get a maximum point. So my answer for the maximum point and the maximum value is none for each. For the coordinates of the minimum point, I know the x coordinate is -1. I need to do the math to get the y coordinate. So the y coordinate of my minimum, I use the original function and plug -1 in. I do the original function evaluated at -1, which is going to be 6 times -1, e to the -1. That's -6 e to the -1, and I would write that as -6 over e. Make that e to the -1, 1 over e. So my relative minimum point is -1, -6 over e. The relative minimum value, let's get really lazy and say it's y equals -6 over e, which occurs when x equals -1. There's guaranteed to be an e problem just like that. Maybe it's 5xe to the x or 2xe to the x, but it's going to be structurally just like that. And it's only first derivative tests, increasing, decreasing, maximums, and mins. We won't do any second derivatives with the e's on the test. Here's another just look at the picture. Find out where the graph is concave up, concave down, and the inflection point. And I only put the inflection point on here to make it not confusing. So I'm going to separate this graph to the portion to the left of the marked point and to the right of the marked point. To the left of the marked point, it goes from the far left edge of the x-axis, which starts at -infinity, ends at the x-coordinate of that point, which is 5. Second interval starts at the x-coordinate of the marked point 5, goes off to infinity. This region here is a concave down, because you can see that it's kind of cupped down here. This region to the left of that point is a concave down, and then the right of the point, that's a concave up. Since the graph is switching concavity and that's a point on the graph where it's continuous, that's an inflection point. So for the graph is concave up, it's concave up in the interval 5 to infinity. concave down in the interval negative infinity to 5. And that single point, 5, negative 16, that's marked as the inflection point. No algebra. You wouldn't even have to draw any of this in. You could just write the answer straight down without doing any work there. There's no work that needs to be shown there. Problem 4 gives me a polynomial, and it only asks me second derivative questions, kind of out of section 3.3. So I need these concavity answers. I need the second derivative. So to do 4, I need one giant computation to get all the answers. First, I'm going to find the first derivative using the nice power rule. The derivative of x cubed is 3x squared. The derivative of minus 30x squared is minus 60x. Not good enough to stop there because I'm doing concavity. Concavity needs the second derivative. The second derivative is going to be 6x minus 60. Once I get the derivative, second derivative, I set it equal to 0 to get my critical values. In this case, I'll set 6x minus 60 equal to 0. I'll add 60 to both sides and get 6x equal to 60. Divide by 6 and get my critical number of 10. I'm going to plot that on a number line that has negative infinity on the far left edge, positive infinity on the far right edge. Create my intervals with round parentheses, negative infinity to 10, 10 to infinity, and plug numbers in. In this interval, I'm definitely going to plug in 11. In the first interval, I probably can get by plugging in 9, but 0 is going to be easy to do in my head. I can kind of work ahead of time, but it doesn't matter. If you plug in 9, that's fine. They're going to give different results, but the results will have the same signs. So first interval, plug in whatever number you pick. I picked 0. Usually I pick 0 unless it's a fraction. And this gives me negative 60, which means in that interval, the graph is concave down. If you picked 9, you'd get negative 6. It still would tell you the graph was concave down. When I plug 11 in, I get 6 times 11 minus 60. That's going to give me 6, and because it's positive, the graph is concave up. So the graph goes from concave down to concave up. 10 is a point where the graph is continuous. This is the x coordinate of an inflection point. So let me write some of these answers. The graph is concave up in the interval from 10 to infinity. The graph is concave down in the interval from negative infinity to 10, and the x coordinate of the inflection point is 10 because the graph changes in concavity on either side of 10. Let me get the y coordinate. The y is going to be found by plugging in 10 to the original function, so it's going to be 10 cubed minus 30 times 10 squared. So it's 10 cubed minus 30 times 10 squared, and I get negative 2,000. So my inflection point is the point 10, negative 2,000. That would be a nuisance to show on a calculator. I'd have to make my y min, probably like minus 4,000 to make it more clear. But that's everything for 4. 5 is a polynomial. Pull out all the graphing questions from section 3.4. So eventually I'm going to sketch a graph. So I'm going to pull out a blank sheet of paper to start sketching that graph right up. And as I find features of the graph, I'm going to plot them. At least as I find points on the graph, I'm going to plot them. So first I need to find the x-intercepts, and I think I actually get a square root. Didn't get that in the homework that I did on the video, but this is okay. I'm going to set the function equal to 0. We get some new algebra, which I don't generally like to do on the review, but I'm dealing with it. Here I'm going to factor out an x. And I didn't make this factor so nicely because all of a sudden it made the calculus part ugly, and I wanted the calculus part to be clean. So now I'm going to set x equal to 0. And I'm going to set x squared minus 3 equal to 0. That I can't factor because 3 doesn't not a perfect square root. I'm going to add 3 to both sides. This is a skill that we teach in intermediate algebra and college algebra. And then I'm going to square root plus or minus square root. This, the reason this is really on there is because so many students try to just use their calculator on the test to get answers. And I don't want to give any credit for that. And this is supposed to defeat that as much as anything. So I square rooted the x squared and got x, and then plus or minus the square root of 3. So my x-intercepts are 0, 0, positive square root of 3 comma 0, and negative square root of 3 comma 0. I have to gauge where to graph these, so let me figure out a decimal for the square root of 3. So second square root of 3, I get 1.73. So on my x-axis, I need to plot the point positive 1.73, negative 1.73, and 0. So here's the point 0, 0. That's a freebie. And then 1, 2, and negative 1, negative 2. Negative 1.73 is about there. That's I'm going to call negative square root of 3 comma 0. Positive 1.73 is about there. I'm going to call that positive square root of 3 comma 0. That would be really hard. You couldn't get it on my calculator. It wouldn't ever give you that answer as a square root. Part B, finding the y-intercept, I just plug 0 in for x. I get f of 0 is 0 cubed minus 3 times 0, and that's just going to come out to 0. The y-intercept's already marked, so I don't need to go and remark it. Now, all of the first derivative stuff. So I need the function. The function is x cubed minus 3x. I'm going to find its derivative, get my critical values, and do all the stuff I can on my number line. So f prime of x equals 3x squared minus 3. I need to get my critical values. I'm going to set that equal to 0. I'm going to factor out a common factor of a 3 and get 3 times x squared minus 1 equals to 0. So the reason those x-intercepts were so ugly is to make this come out nice. So factoring it all the way, I get 3 times x plus 1 times x minus 1 equal to 0. Setting the 3 equal to 0 won't give me a solution because there isn't an x. Setting the x plus 1 equal to 0 gives me a critical number of negative 1. I would minus 1 from both sides. Setting x minus 1 equal to 0 gives me a critical number of 1. I would add 1 to both sides. Plot my critical numbers along with infinities on a number line. Create my intervals. So I'm going to go from negative infinity to positive infinity, stopping at negative 1 and 1 between. Create the interval from negative infinity to negative 1, the interval from negative 1 to positive 1, and the interval from 1 to infinity. In each interval, I need to pick a number. In the far left interval, I'm going to pick negative 2. In the middle interval, I'm going to pick 0. And in the far right interval, I'm going to pick positive 2. Plug them into this derivative. I like plugging them in right there. It looks easy for my calculator. So I'm going to do the first derivative evaluated at negative 2 is 3 times negative 2 squared minus 3. This is 3 times 4 minus 3. I'm going to not do this on my calculator. That's just 9. And then f first derivative evaluated at 0 is 3 times 0 squared minus 3. This piece comes out to 0, and 0 minus 3 is negative 3. You can do these on your calculator. I'm just trying to save a second. And then when I plug in 2, I get 3 times 2 squared minus 3. This is going to be 3 times 4 is 12, minus 3 is 9. So first interval, the graph is increasing because I get a positive. Middle interval, the graph is decreasing because I get a negative. Last interval, the graph is increasing because I get a positive. So my answer to C, I don't know what number this is anymore. I think this is 5. So for 5C, this graph is increasing in the outside intervals. negative infinity to negative 1, union 1 to infinity. For 5D, it's decreasing in the negative 1 to 1. And it doesn't call out for the maximum and minimum value. It just wants the points. I'm not going to, for the graphing, it's enough to get all this junk done. And let me find out where I have maximums and where I have minimums. So the graph goes increasing, decreasing, increasing. So at negative 1, there's a maximum. And at positive 1, there's a minimum. So the x-coordinate of the maximum, which is for part E, is negative 1. The x-coordinate for the minimum is positive 1. And now I'm going to get the y's. I'm going to do f of negative 1 equals negative 1 cubed minus 3 times negative 1. Better do that on my calculator. Lighting it just depends on the time of the day where my calculator needs to set. So it's like late afternoon and it doesn't want to sit anywhere. So my maximum point is going to be the point negative 1, 2. And now I'm going to eventually plot that. My minimum point is going to be 1 cubed minus 3 times 1. That's just 1 minus 3, which is negative 2. So I have 2 points now to plot, a maximum point and a minimum point. So once I get points, I plot them. Intervals, I'll get to show when I finish up the graph. So I'm going to plot the point negative 1, positive 2. That's a maximum point. And positive 1, negative 2. This is a minimum point. So boy, I can have a really tight window here, I imagine. Positive 1, negative 2 is my minimum point. Let me just scribble that out. Okay, now we need the second derivative information for g, h, and I. So I'm going to carry these derivatives here. The original function is x cubed minus 3x. I have the first derivative. I'm going to use the first derivative to get the second derivative. The derivative of 3x squared is 6x. The derivative of minus 3 is 0. So the derivative I need for the concavity problems is just 6x. That's just the derivative of the first derivative. So I'm going to set that derivative equal to 0. Divide by 6, divide by 6. Get a critical number of 0. So on my number line, I'm going to put infinities in 0. Real easy testing. I won't need my calculator for this. Create the interval from negative infinity to 0. The interval from 0 to infinity. In this first interval, I'm going to check negative 1. In the second interval, I'm going to check positive 1 right into that first derivative. So I'm going to evaluate the second derivative at negative 1 and get 6 times negative 1, which is negative 6. Evaluate the second derivative at positive 1. That's 6 times 1, and that's positive 6. This is concavity, so if you get negative, it's concave down. If you get positive, it's concave up. So my answer to part G is concave up from 0 to infinity. My answer to part 5H, it's concave down from negative infinity to 0. And then since it's switching concavity, and this is part of the domain, it's going to be continuous there. This is going to be an inflection point. So the inflection point's x-coordinate is going to be 0. I've already done the computation for the y. Doing f of 0, you get 0 cubed minus 3 times 0, which is going to be 0 for the inflection point. Lastly, I just have to sketch a graph. And what has to happen is to the left of the maximum point, well, let me just borrow this on my calculator and talk us through it. So I'm going to really scrunch my window down here. For my function in my y1, I'm going to enter the equation that we were given, which is x cubed minus 3x. And I'm really going to focus down because everything's happening around the origin. I think I'm going to make everything negative 5 to 5, and that might even be not narrow enough. But negative 10 to 10 feels like my minimums in my maximums and my inflection points might not show up as nice as I like. So I'm crunching it down to the 5s just because everything's happening in between -2 and 2. If I did between -3 and 3, that would be equally fine, maybe even better. So crank out my y equals. So y equals clear x up arrow cubed minus 3x, window -5 to 5, -5 to 5. Graph it. And here's what happens. The graph increases and it's concave down, goes through the x-intercept, continues to increase, stays concave down, gets to the maximum point of -1, 2, stays concave down all the way to the inflection point at 0, 0, which is also an x-intercept. So it's increasing in concave down until it gets to the maximum point. Then it's decreasing in concave down until it gets to the inflection point. Then it's decreasing in concave up till it gets to the minimum point, and then it's increasing in concave up the rest of the way. So it's concave down to the left of 0, 0, it's concave up to the right of 0, 0, passes through all three intercepts, it increases between -infinity and -1, it decreases between -1 and 1, and it increases between +1 and infinity. That feels good. We're at 26 minutes. Let's see where we're at here in terms of what the next problem is. I think we should break up part 2 just because the next problem is the full out graph of a fraction, and that's got to be more than a few minutes. So let me pause and we'll do a part 2 to this video.